This is the last video in our series on coded compressed sensing, and in this module we want to draw a strong connection between coding and compressed sensing through approximate message passing. We also want to review very recent results in this area, and we want to outline possible avenues for future research as well as interesting open questions. By now you should be very familiar with the compressed sensing scheme and its divide and conquer approach, where every device starts with a binary message, it adds parity bits to it, and then the encoded vector is partitioned into blocks, and every block is sent separately during a slot. Messages from the different active devices are added up over a multiple access channel, and the receiver takes the observation, runs a compressed sensing solver, and produces a list of k items for every slot. These lists are then passed to the tree decoder, where the redundancy embedded in the various blocks is used to stitch the different fragments together and recover the original messages sent by the active devices. This is illustrated on this slide with a graphical representation of the stitching process through the tree. One view of the coded compressed sensing scheme is to view the sensing matrix as a block diagonal matrix, one block for every slot, and to view the messages sent by every device as a concatenation of sections, each of which is one sparse. In this graph, we have the block diagonal structure of the matrix times the vector, and this leads to the received signal after the messages are added up over a multiple access channel. An important point about this scheme is that the complexity reduction not only comes from the block structure of the sensing matrix, but it also comes from the length reduction in the message vector from the devices. The reduction goes from a vector that was originally one sparse of length 2 to the m to a vector that has L non-zero entries, one per section, of length 2 to the m over L. This viewpoint was recognized by Fengler, Jung, and Caire, who based on this reduction in length argued that the sensing matrix A, instead of having a block sparse structure, could then be dense since the number of columns was smaller. This dense sensing matrix provides a foundation for their Sparks and M for unsourced random access scheme, which was presented a year ago. In their scheme, they run approximate message passing using the whole matrix to recover an aggregate sparse vector that was transmitted over the channel, and then they pass that vector to the tree decoder for message recovery. A second improvement we've seen to coded compressed sensing is the notion of column pruning. In this scheme, lists at the early stages of the process are used as side information to help the recovery task at the later stages. This is achieved by keeping track of all the active paths obtained so far, computing the set of parity patterns for these paths, and pruning the matrix of any column that doesn't fit within this set. If we were able to use the structure of the tree code in the decoding of the coded compressed sensing, it would seem that we can also do so while using approximate message passing. Specifically, what we would like to do is get the best of both worlds. We would like to use a full matrix with approximate message passing to improve performance, and at the same time we would like to leverage the structure of the tree code dynamically so that the information can propagate and assist the decoding process. There are a few problems with trying to do that. One of them is that in this setup, there are no columns to prune. And the other problems is decisions are not made in sequence. So there's a bit of a mismatch between the two techniques, and we need to do some work to be able to take advantage of this structure. The rest of the video focuses on how this can be done, and to understand how we can bring the two together, we start by looking at the equations of approximate message passing again. So here we have the two composite equations The one at the top is the computation of a residual, and hence with an Onsager correction term, and the second one is the effective observation that's obtained through the process. Note the presence of the denoiser in the second equation, which is there to capture the structure of the signal. We would like to put the information we have about the tree code in the denoiser. But first, let's review how Finkler and his co-author were able to identify a low complexity denoiser suitable for approximate message passing in the context of unsourced multiple access. The proposed denoiser is a marginal posterior mean estimate. And what it does is it computes the expectation of a single component that can be either a 0 or 1 embedded in noise. You get an equation of this form, which is based on the likelihood of a binary signal in Gaussian noise. Variable Q acts as a prior for the marginal posterior mean estimation, and it's simply the number of non-zero entries divided by the length of the section. The denoiser is then obtained by aggregating the entries together per section and concatenating the sections together. In this equation, there's a variable tau that corresponds to the standard deviation of the noise, and this can be approximated through this equation. There's also PL, which denotes the power used in that particular section. While computationally simple, this denoiser is quite successful at applying approximate message passing to the problem at hand. What we would like to do is retain the lessons from Sparks and AMP for unsourced random access, use approximate message passing for coded compressed sensing, but embed the information that's afforded by the tree code into the denoiser. And to do that, we need to look at the structure of the tree code a little bit more closely. On this slide, we see the structure of the tree code, where parity bits are created as linear random combinations of information segments that precedes them. And in particular, we look at the parity bits associated with slot 5, and we see that to create these parities, we use the information segment from slot 1, 2, 3, and 4. This Markov structure was very successful at keeping the complexity low for the tree decoding process that started from a root and progressed down the tree towards the leaves. However, it's not very suited for approximate message passing. The challenge is that in the denoiser, we must pass information about the beliefs of entire sections, and this is much larger than keeping short lists of candidates that have been decoded so far. Computing site information for entire sections with this particular tree graph is very difficult. We therefore seek a different structure that's amenable to low complexity belief propagation. In doing so, we would like our denoiser to have the following properties. We must be able to compute belief on the order of the section length, say on the order of 2 to the 16. We must provide pertinent information to the approximate message passing algorithm, and we should also be able to stitch the fragments together at the very end of the decoding process, as this will be the last step again. There's a number of tricks that we can use to keep complexity low when it comes to message passing. One of them is to use the sum product algorithm on the factor graph, and another one of them is to have a parity structure that's conducive to the application of fast Fourier transform technique. We propose to use both. So in this figure, we have a graphical rendition of the type of factor graph we have in mind. The nodes S1, S2, S3, and so on are the variable nodes, and these are vectors of length 2 to the 16, which captures the belief that a particular device is sending a specific block. The nodes on the left are the local observations that are processed into a message, and the nodes on the right are the factor based on the parity structure. The creation of parity bits is modified slightly to be able to leverage a circular convolution structure, and with this structure, we're able to apply FFT techniques. The message passing equation here is somewhat standard, where the message from factor node AP to variable node SL is computed as follows. The factor node aggregates the probability on all the parity consistent paths, adds up the extrinsic information, and sends it back to the variable node component-wise. Since the parity bits have a circular convolution structure, this can be achieved by taking first the Fourier transform of the incoming messages, the product of these Fourier transforms, and then sending the inverse FFT of the extrinsic information back to the variable node. The leading coefficient, this 1 over the 0 norm of GLP, accounts for all the locations that match a particular pattern. In this sense, the weight of the beliefs that's computed at the factor node is split among all the locations that match this pattern. This hints at the fact that we want to use a tree code that doesn't have too many locations that match a same pattern. Another consideration is what we call mixing. We have several messages being passed on the same graph, and there has not been stitching yet, so the message passing algorithm does not know which fragment goes to which other fragment. To illustrate what happens, we look at this simple example. Suppose that messages have concentrated on 2 locations in slot 1, and messages have also concentrated on 2 locations in slot 2. The third slot is the parity pattern associated with slot 1 and 2. The 2 parity patterns in the first slot will combine with the 2 parity patterns in the second slot to create 4 strong patterns for the third slot. For instance, 0 and 2 will lead to 2, 0 and 1 will lead to 1, 2 and 1 will lead to 3, and 2 and 2 will lead to 0. So there's a multiplicative effect of the concentrated distribution from section 1 and section 2 in terms of the numbers of elements that are strong in the third slot. This suggests that the factors in the redesigned tree code should be acting on a small number of sections. What we propose to use is what we call a triadic design, where every parity section acts on 2 information sections. This way, there's not too much mixing, and we're able to see concentration being passed from 2 slots to a third slot. We can summarize the redesign of the tree code as follows. The parity bits are now generated as an abelian group, which is amenable to fast techniques such as the Hadamard transform or the fast Fourier transform. This enables us to pass beliefs on very large sections. We also want the factors to act on a small number of sections, and this is to make sure that the information that's being propagated through the graph remains meaningful. We want to avoid too much mixing, and we want to be able to propagate concentration. To achieve that, we have uniform sections that contain either only information bits or only parity bits, and we place the parity section in between information bits. The triadic designs that we propose, the parities are acting over only 2 blocks of information section. Altogether, we have a tree structure that looks like the figure at the top of this slide. Here the information blocks are in light gray and the parity blocks are in dark gray. You can see that the parity sections are attached to only 2 other sections, which will enable us to pass meaningful information. And you can also see that we've avoided short loops for the belief propagation. We've added the message passing equations, which are admittedly somewhat obscured, The top one are the messages from the factor nodes to the variable nodes. And the G factor here is making sure that the parities are consistent with the message. The product is over the extrinsic information. The bottom equation is from the variable nodes to the factor nodes. And this is the product of the belief vectors coming from sections that are involved in forming certain parity patterns. If you are already familiar with belief propagations on factor graph, then these equations should not be too surprising. Otherwise, you'll have to take our word for it that we can pass information within the denoiser using these equations. On this slide, we have the updated equation for approximate message passing with the side information from the tree code coming from belief propagation. The two equations look surprisingly like the original one, with the top being the residual plus the correction, and the bottom one being the effective observation. The difference between the original scheme and our approximate message passing scheme is really hiding in the denoiser. What we do here is we take the effective observation section by section, we kick it back to the belief propagation algorithm, we run a few rounds of the factor graph, often just one step, we get the state estimate from that, and then we put it back into the update of the effective observation. Although we're not showing it, the computation of the correction term is a little bit more involved. But the interesting thing is that provided that the number of cycles you're performing on your belief propagation graph is smaller than the shortest cycle on your graph, then the computation of the correction term remains somewhat straightforward. On this next slide, we see the performance of the enhanced approximate message passing for a coded compressed sensing scheme. On the left graph, the x-axis is the number of active users, and the y-axis is a performance criterion expressed in terms of a required EB over N naught to meet a certain probability of failure requirement. We have three curves. In blue, we have the performance of the original AMP and Sparks for random access. In green, we have a curve of the enhanced AMP technique that leverages the belief propagation on the tree. And at the bottom, we have a competing sparse IDMA, which also performs quite well. On the right side, we have a comparison of the complexity between the original AMP for Sparks and the enhanced version where you do the message passing. The x-axis is the number of active users, and the y-axis is the average runtime. You can see that the gap between the two is not that big, which is very encouraging. These results are fairly recent, and we've not had time to explore the full parameterization of the coded compressed sensing with approximate message passing. It is possible that after optimization of the tree parameters, performance will improve. In summary, we have presented a new connection between coded compressed sensing and approximate message passing, where the denoiser dynamically leverages the structure of the tree code to improve performance. In building this algorithm, we had to revise the tree code to make sure that we can pass beliefs on very large vectors, and we did that by embedding a circular structure into the creation of parities, and then applying a fast Fourier technique. The lessons for the tree code design includes the fact that the degree distribution of the factors should be small. The size of the section should be big to avoid collisions. And the tree code should be built in such a way that the final step, the stitching process, is still possible. At this point, there are many theoretical and practical challenges with this scheme. It may be possible to do a joint analysis of the convergence of approximate message passing and belief propagation in the denoiser. We also need to explore a factor graph beyond the triadic design we've proposed. And we can look at variations like cascading, power allocations, or explore the impact of fading. As a final note, we point out that the performance of the approximate message passing for unsourced random access seems to benefit from integrating lessons from coding theory. This is not too surprising since CCS was originally designed for a multiple access channel, yet it's nice to see the evolution of the scheme over time. This is essentially what we want to cover about approximate message passing for coded compressed sensing. And next I will turn it to my colleague, Krishna, who will talk about schemes that are more heavily rooted in coding techniques.